Snap a photo of a handwritten note, a messy spreadsheet, a chart in a report, and an AI can read it back to you. So picture what is happening inside. There must be an eye in there, a little camera, a vision part that looks at the picture the way you do. That is the natural assumption, and it is wrong. The model has no eye. There is no looking, no glance, no gaze. What it actually does is stranger, and it has a price tag. It chops your picture into a grid of small squares, turns every square into the very same kind of token it uses for words, and then reads your image like a sentence. And here is the part nobody tells you up front. Those image tokens are not free. They land on your bill right next to the words. So the same photo, sent two different ways, can cost you dozens of tokens or thousands. Today, we look at exactly how a model sees and why seeing costs you. Start with the move itself, because it is the same move you already know. Back when we taught text, a sentence was too big to swallow whole, so we cut it into tokens. An image is the same problem, bigger. You cannot pour a whole photo in at once, so you cut it into pieces. Lay a neat grid over the picture and slice it into a checkerboard of little square patches, each one a fixed size, often around 16 pixels across. That word patch is the real term, and it is the whole trick. This patch is a scrap of sky. That one is the corner of an eye. This one is a bit of text on a sign. Then a part called the vision encoder looks at each patch on its own and turns it into a list of numbers, a vector, a point in a space of meaning. This encoder is itself a transformer, the same architecture from Season 1, just fed patches instead of words. People call it a vision transformer, a VT, and crucially, it is not memorizing the raw pixels. It is summarizing what the patch contains. A photograph just stopped being pixels. It became a grid of points. Now notice the immediate consequence, the one that will cost you later. A bigger, sharper image has more patches. More patches means more points. So resolution is not just detail. It is quantity. Hold on to that, because the bill is hiding inside it. Now we have a grid of image points and a separate stream of word points. They came from totally different worlds. How do you get them to talk? You build a small translator, usually nothing fancier than one or two layers of a little neural network, called a projector or a connector. Its only job is to take each image point and nudge it into the exact same space of meaning the words already live in. That destination has a name from Season 1, the shared embedding space, and that is the whole secret of multimodality. After the projector, an image patch and a written word are the same kind of object, the same length, sitting in the same room. And once that is true, the machinery from Season 1 just works, for free. Remember, the part of the model that reads is completely indifferent to where a token came from. It eats a sequence of points and hunts for relationships in them. So you simply slide the image points into the line right alongside the words. The photo becomes a passage in the text. Now when you type, "What is wrong in this chart?" the word "this" can physically reach across and attend to the patches of the chart, exactly the way one word attends to another. No second brain. No bolted-on vision module. The same reader, reading one longer sentence that happens to be part picture. So an image is now a run of tokens in your sequence. Providers call them image tokens or visual tokens, but they bill exactly like the words. And tokens, as this season keeps reminding you, are the unit you pay for, and the unit that fills your context window. Which means a picture is a line item. Here is roughly how providers count it, and the shapes are remarkably similar even when the exact numbers differ. A tiny or low-detail image often gets a flat, cheap price, just a handful of tokens, because it is squeezed down to a few patches. But ask for high detail, and the provider does something specific. It scales your image up and lays a grid of square tiles over it, a step called tiling, and every tile costs a fixed block of tokens. So the bill is a floor plus a tile charge. There is always a minimum, a floor, one tile at least, and then the cost climbs in steps, tile by tile, as the picture gets bigger and sharper. Some newer systems skip the tiling and just charge you per fixed size patch directly, up to a per model cap, but the lesson is identical. Pixels become patches, patches become tokens, tokens become money. The image you thought was one tidy attachment is, on the inside, a paragraph you are paying for by the word. Now the hook, the thing worth burning into memory. The same photo, the literal same file, can cost you wildly different amounts depending on one tiny choice. Send it small or at low detail and you might spend a few dozen tokens. Send that identical image at high detail or at full resolution and you can spend hundreds, sometimes into the thousands. Same picture, same content. Often a tenfold difference in price and a matching dent in your context window, decided entirely by a knob most people never touch, a setting providers literally call the detail or the media resolution. Different providers use different math, and they quietly revise the numbers over time, so do not memorize a figure, memorize the shape. There is a cheap flat mode for when you just need the gist. There is an expensive detailed mode for when you need to read the fine print. And the practical takeaway is real money and real speed. If you are pushing thousands of images through a system, downscaling the ones that do not need detail, or flipping that knob to low, can cut your cost and your latency without hurting the answer. Knowing the picture is secretly a pile of tokens is the whole reason you would think to do that. There is one more fork in the road, and it changes whether images even touch your budget. Most modern open models do what we just described, called early fusion or token concatenation. The image tokens are dropped straight into the sequence, shoulder to shoulder with the words. That is simple and powerful, but it has a cost beyond money. Those image tokens occupy your context window, and they sit in the model's working memory, the thing this season called the KV cache. A few high-resolution photos can eat a big slice of the room you had for actual instructions. But there is a second design. Instead of putting the image into the line, you keep it off to the side and add special layers whose only job is to let the words glance over at the image when they need to, while the original language model stays untouched. This is called cross-attention. The picture is still there, still being read, and it is not free to run, but it is not sitting inside your main sequence, so it does not crowd out your text the same way. Two honest trade-offs. Early fusion is simpler and lets every word mingle freely with every patch, but the image spends your context. Cross-attention guards your context at the price of a more specialized, less flexible design that has to be bolted on rather than coming for free. Neither is the universally right answer. They are different bets, and the model you happen to be using has already placed one for you. So where does all this actually pay off? The killer use case, the one quietly transforming offices everywhere, is reading documents. A receipt, an invoice, a scan contract, a chart in a slide, a page of handwriting. And this is a genuine before and after story. For decades, getting text out of an image, the task we call OCR, meant a brittle assembly line. One tool to find the words, another to straighten them, another to guess the characters, and the whole thing fell apart on a weird font or a two-column layout. Then the patch token approach arrived. Because a document is just an image, and an image is just tokens, the very same model that chats with you can now look at a full page, tables, equations, columns, and all, and write out clean structured text in one pass. That is what people mean by end-to-end document understanding. The whole brittle pipeline collapsed into a single model. The old line that an AI cannot read a chart or a messy receipt was true, and then it stopped being true fast in just the last couple of years. On the standard document benchmarks, the best models now score in the low 90s out of 100, close enough that researchers have had to invent harder tests. It is not magic, and it is not perfect. Tiny fine print, rare scripts, dense multi-column pages, and a stray digit in a long number can still trip it, which is exactly why you check the output that matters. But the direction is unmistakable. Reading the visual world is no longer a separate specialty. It is a side effect of turning pictures into tokens. So let us put the whole thing back together. A model does not have an eye. When you hand it a picture, It lays a grid over it and slices it into patches. A vision encoder turns each patch into a point in the same space of meaning where words already live. A small projector slides those points into your token stream, so the photo becomes a passage the same reader reads. And because they are tokens, they cost. A floor plus a tile charge, the same image cheap at low detail and expensive at high, eating real money and real space in your context window, unless the model keeps the image off to the side with cross-attention. The senses were never a separate organ. Seeing for these models is just reading with pictures turned into words first. So the next time an app charges you for an image, or an answer about a photo comes back a little vague, you will know exactly why. You did not send a picture. You sent a paragraph of tokens, and you got billed by the word. Next, we follow those tokens deeper into what it actually costs to run one of these models at scale.